So we have found the arc length in rectangular coordinates. Remember, that was the square root of 1 plus dy dx squared with respect to x. We've also found the arc length in parametric mode, which is given right here. And now, of course, we have to find it in polar coordinates. So remember, r is a function of theta. We're going to bound that between two angles, so we have a definite length to find. And we also have to make the condition that our derivative of r is continuous on that interval. So that seems easy enough. Since we're in polar coordinates, we just change the variable and we're done. But aren't we? Can we do some more simplification? I think so. So remember that x equals r cosine theta and y equals r sine theta. Let's see what we can do with this formula. So the first thing I'm going to do is I'm going to find dx d theta. And remember that r is a function of theta, so I'm going to have to use the product rule. So I'm going to have the first times the derivative of the second plus the second times the derivative of the first, and I'm just going to use that prime notation. So now I need to square it because of this. So if I square this, I would have to FOIL it out. So I'm going to have r squared positive sine squared theta. Then multiplying those together twice, I'd have minus 2r, the derivative of r, sine theta cosine theta, then plus the derivative of r cosine theta all squared. And you're saying, hey, you're supposed to simplify it, not make it worse. I know, just hold on. So now I have dy d theta. So again, the product rule. So I have the first times the derivative of the second plus the second times the derivative of the first. And I'm going to square that out. So I have r squared cosine squared theta plus the middle terms plus the last term squared. So what does this formula say to do with dx d theta squared and dy d theta squared? It asks us to add those together. So let's do that. So dx d theta squared plus dy d theta squared. Are there any like terms? Yes, there is. This and this are exactly alike, but opposite in sign, so those add to 0. So I add these two. They both have an r squared. So I'm going to write this as r squared times sine squared theta plus cosine squared theta. And now you can see where I'm going. Right? These have an r prime squared in common, and they would be cosine squared theta plus sine squared theta. And we all know what that equals to. That equals to 1. So our dx d theta squared plus dy d theta squared can be reduced to our function squared plus our derivative of our function squared. So now we can write that the arc length is equal to the integral evaluated between alpha and beta of the square root of r squared plus dr d theta squared d theta. And now it looks a little bit better. And it's all in terms of r, which is quite helpful. So now let's apply that formula. It's not too bad. Find the length of the curve over the given interval, and they're giving you a function, and they're giving you that interval. So our length is going to be between 0 and pi of the square root of r squared plus the derivative of r. And then we have to square that. So let's take the derivative of r. So the derivative of 1 is 0. The derivative of cosine is negative sine theta, and if I were to square that, that would be positive sine squared theta. And I have to evaluate that integral. Well, let's see where that leads. So we have the square root of, I need to square this out. And once again, that is equal to 1. So I have that 1 plus that 1 is 2. So I have 0 to pi, the square root of 2 plus 2 cosine theta d theta. How do I integrate that? Now that is a tough question. We have to do a little bit of maneuvering. We can't just use u substitution because I have a cosine of theta. I don't have the derivative of that. But let's see, I could look at this as 2 plus 1 times the cosine of theta. What does that look like? Kind of like some identity. So let's go over here. And let's see, I kind of remember that cosine squared theta equals to 1 plus the cosine of 2 theta divided by 2. This kind of looks like this, except for the 2. And then I kind of remember that, you know, those just have to be double each other. So could I write it a different way? Could I say the cosine squared of half theta equals to 1 plus the cosine of 1 theta divided by 2? Right? Those two angles just has to be this one multiplied by 2 is this one. So this times 2 is that. Well, that almost matches. Now if I multiply both sides by 2, 2 cosine squared of 1/2 theta would equal to 1 plus cosine theta. That's what I'm going to use to substitute in. Let's see if that's going to help me out at all. So my arc length from 0 to pi is the square root of 2, because remember I factored out the 2, and in place of 1 plus cosine theta, I'm going to substitute in this, 2 cosine squared of half theta. Okay, I've got squares. I can take the square root. That is good news. So let's see. 2 times 2 is 4. The square root of 4 is 2. So I'm going to pull that out of the integral. The square root of cosine squared is going to be cosine. And remember, I'm integrating between 0 and pi. I can integrate cosine. The integral of cosine is sine. All right, so I've got the 2 on the outside. The integral of cosine is the sine, and I keep the angle. But now I've got to be careful. Because of this 1/2, I have to divide by 1/2, which means I multiply by 2 over 1. And remember, I'm going to go from 0 to pi. So I have 4 times the sine of half theta between 0 and pi. So 4 times the sine of half pi minus 4 times the sine of 0. Well, the sine of 0 is 0. The sine of 1/2 pi, 90 degrees, is 1. So that's just 4 times 1, which is 4. So all that work to find out the arc length is just 4.